Okay, so as I said, the next two lectures will be just about birational geometry of blow-ups of projective spaces at points. And I recall that the Cox rings of these spaces are Nagata invariant rings. So they are invariant rings of the so-called Nagata action on a polynomial ring of certain additive groups. And so I want to see what can we, if you look into the geometry of these spaces, how can we see that the Cox ring is or is not finitely generated from the geometry? Yeah, so birational geometry of these spaces, by this I mean study morphisms and rational maps of these spaces and how this translates into our understanding of the birational geometry cones of like Neff divisors and movable divisors and effective divisors. So I will work over an algebraically closed field. Eventually this may have to have characteristic 0, but not for the moment. So X will denote such a blow up. So Pn blown up at k distinct points. Right. So far I only say they're distinct. And so what do we know about these? So when k is small and the points are in linearly general position, these are toric. Yeah, so I will remind you that if k is at most n plus 1 and the points are in linearly general position, so no n plus 1 of them are lying on a hyperplane, then this is toric. And then the next case is these are if the points are in general position, so a bit more than linear we impose now, but still it's a finite set of conditions, then so this can be made precise. Then the X is a Mori dream space, which is non-toric. This is a consequence of the theorem I mentioned last time. So let's say the case of k equal n plus 2, this is classical, but the Cox ring is an invariant ring for the additive group, just one copy of it. So yeah, so by Weizenburg's theorem, this would be, in characteristic 0, this would be finitely generated, but it's also a well-known ring. It's a homogeneous coordinate ring of a Grassmannian. And this one was the main content of the theorem, that this is isomorphic to an invariant ring for the two-dimensional additive group. And this is a Nagata invariant ring which is finitely generated. Okay, and so, and the ring is more complicated, but it can be understood in terms of generators. And there are even conjectural relations. So the next case, k equal to n plus 4, is a case I will concentrate on a bit later. So here I want to assume that the points are very general. So I will explain exactly what we need. And so in this case, again, the same theorem of Mukai tells us this is not a Mori dream space. This is a variety with the Cox ring, which is an invariant ring for the three-dimensional additive group. So this is for not a Mori dream space if n is at least, the dimension is at least 5. Okay, so in a way you can think of this as the simplest non-Mori dream space. And then I want to revise now a bit the case of surfaces. So yes, I want to look at the case of surfaces. So now S is a blow-up of P2 at k points, k distinct points. Again, let me repeat. So if k is at most 3 non-collinear points, this is toric. If k is between 4 and 8, and the points are general, so this just means that in addition to non-collinear, no 6 of them are on a conic, and when k is equal to 8, You also don't want any cubics through 7 points with multiplicity 2 at one point. Then in this, so this is a del pezzo. Yeah, so minus k is ample. Okay. And then I want to make a remark that this is true for any k. That if you have by a junction, and you have a curve on a surface, let's say an irreducible curve, okay, then if c times k is negative and c squared is negative, then this must be a -1 curve. So just because the arithmetic genus is non-negative, so it has to be 0, so it has to be a P1 with self-intersection -1, intersecting k and -1, and C is a P1. So a so-called -1 curve. Okay, so I want to recall you Maury's cone theorem. That so now recall that we're looking at the cone of effective divisors, the closed cone of effective divisors. Yeah, so this is inside the Néron-Severi vector space, which in this case it's just yeah, the linear equivalence of divisors is the same as numerical equivalence. So, yes. So I'm just looking at Picard group tensor with R. So I will look at all the effective combinations of curves on S, and then we close this up. This is a Maury cone. And so the Maury cone, the cone theorem tells you that there is a part of this cone, namely the k-negative part, that we understand pretty well. So on the k-positive side, this does not attempt to say much, but on the negative side, they are only the k-negative curves with self-intersection, only the -1 curves that appear here. Look at, okay. Let's see. Okay. And then I also want to say that this is also, there is a variant of this where you look at, where you throw in an ample divisor. And then if I take, I have the same statement. So the positive part of k plus a small multiple of a. Positive part with respect to this divisor, and then the negative part with respect to this divisor will be there will be only finitely many curves here. Okay. Okay. Okay, so, and we also know that on the k-negative side, this cone is locally polyhedral. Okay, so a corollary here is that for del pezzo surfaces, the Maury cone is generated by -1 curves, and there are finitely many of them. Now, yeah, so I want to draw a picture of the Maury cone. So there are several situations when k is at least 9. And here I want to look at the very general point situation. So what does very general mean? So this will mean for us Cremona general. I'll explain. Yes. Yes.
Can you please explain the notation
F. Yes. Okay. So in general, yes. So the closed cone of divisors for any variety x is you take a cone of generated by effective divisors. So these are codimension ones of varieties, non-negative coefficients. And then I close this up. I take numerical classes in the Néron-Severi space. And then...
yes, but when you say there's an index k for...
yes, okay. So I will denote this or whatever, any divisor. These are classes, classes with this property. So it's the upper, I look at the hyperplane cut by one divisor, and then there are positive and negative side, and that's what I mean. Okay, yes? Okay, yes, thank you. Okay, K has to be at least 2 for that to be true, yes. Let's say K is at least 2. Right? Yeah. Thank you. Okay. Okay, so what is very general? So this will mean for me Cremona general. Okay, so in words this means that after any number of Cremona transformations, the points are, no 3 points are collinear. Yeah, so okay, so this is 3 points being collinear. This is a closed condition, but when I require that this is true for any number of Cremonas, this will be countably many closed conditions. So let me recall you that that when you have at least 3 points, yes. So I need for this. Yeah, here I assume k at least 9 for that. But in general, when you have at least 3 points, you can always fix them to be the coordinate points. And then, yeah, so if the points are non-collinear, you can always do this. And then you do what's called a Cremona centered at these points, which after you fix them, this just means that you take the standard Cremona transformation, sending x, y, z to 1 over x, 1 over y, 1 over z. This is called the Cremona center that at these 3 points. So the coordinate lines are sent to points on the other side. And once you blow up the 3 points, this will resolve this map. So the line through 2 points becomes an exceptional divisor for the remaining point when you blow down in the other direction. Okay, and so I want this. I want to look at this kind of condition. Okay, so I want to give an example. I want to give an example of what can happen if the points are not Cremona general. But then, okay, so the point here is that if the points are very general in this sense, and there are at least 9 of them, then there are infinitely many -1 curves. So I will prove this and the generalization of this today. Okay. Yeah, so if the points are all, if they are not general, so if, for example, if they are all on a conic, once you do a Cremona centered at any three of the points that aside from the center of your Cremona, all the other points will line up on a line. Okay, so remark, if I take points on a conic in P2, smooth conic, and then there are finitely many curves on a blow up of P2 at these points. This is not hard to prove. Okay, if I take the proper transform of this conic, of the C, then just using the fact that the anti-canonical is equivalent to this class plus the hyperplane class, so this is the class of a line, you can then prove fairly easily that that the only negative curve is this one. Okay, if you have sufficiently many points, meaning at least 5, and then you have also some -1 curves, but it's not hard to prove that there are finitely many. And then the point is that the Cremona center that at any three of the points will make the points, the remaining points, be on a line. If this is phi, then yeah, the Cremona is a quadratic transformation given exactly by the conics passing through these 3 points. Okay. So I want to draw some pictures for what happens in the very general case. Okay, so let's say k equal 9 very general points. Okay, so I'll prove this next. It's not hard to prove that if you look at the hyperplane cut by k, the only class that's effective here is minus k. You have the class of a cubic through the 9 points. And then you have infinitely many -1 curves which span extreme arrays of the effective cone. Yeah, so this is a locally polyhedral cone. Again, I'm cutting a cross section in it. There are infinitely many rays. It's locally polyhedral. These rays approach minus k, but this is an accumulation point. So this is a cross section of the Mori cone. The light cone I described last time of classes with intersection, non-negative intersection that intersect on a fixed ample class non-negatively is a round cone, but it's contained inside. So what's special here is that minus k is actually an F class with self-intersection 0. Okay, so even if the cone is infinitely generated in this case, you still understand it. And then the cases after that are not understood on the k positive side. So when k is strictly bigger than 9, then you have the hyperplane cut by k. Again, on the k negative side, this is k negative side. So here there are 2 sides. The -1 curves still accumulate. They span extreme arrays of the effective cone, but minus k is not effective, and the points are very general. There is no cubic through all the points. minus k is outside the effective cone. And then here there are long-standing conjectures about how the side on the k positive side looks like. So what's known as in the folklore as the Nagata conjecture, which is due to many people. One formulation is that there is no irreducible curve on this blow-up such that c square is negative and c times k is positive. So in other words, the only negative curves are the -1 curves. And this is quite open. Okay, so yeah, we understand the k negative side and we don't understand the k positive side. And then a point of my lectures will be that this is similar in higher dimensions and it's exactly the same picture. But we do understand the k negative side. Okay. And so now I want to dive a bit more into the cones. What can we say about curve classes on the surface case? There are some simple observations one can do. So I want to list these. Okay, so a lemma, which will be easy to prove. So S is the blow-up of P2 at k points. I will write it like this. K is at least 2. And I will assume here that they are very general if k is at least 9, and general otherwise. So it will also apply to Del Pezzo surfaces. Okay, so the first statement is that, as a simple observation, that if I take a divisor class on S, such that it intersects all the -1 curves non-negatively, then I can write this class as an effective combination of minus k and -1 classes. Okay, so I'll say this is a one-line proof, but then a consequence is that, so this I did not assume that the D is effective or anything, but now you can deduce that any effective divisor, so the effective semigroup, is contained in this span of minus k, which may or may not be effective. I mean, it's effective if k is at most 9, but not otherwise. Okay, and then you can pass to the closure. And so you can say the Mori cone is contained in the span of, in the cone generated by, in the closure of the cone generated by minus k and all the -1 curves. Yeah, so minus k is somewhere out here, but taking combinations of it with the -1 curves passing to the limit, this will produce all the pseudo-effective classes on S. And then also this tells you the shape of the Neff cone on the k negative side by passing through the dual. So by Clemens' theorem, Neff divisors are precisely the divisor classes that intersect the Mori cone non-negatively. The last part of this lemma is that if D is Neff and D times minus k is bigger or equal than 0, or let's say, sorry, if D is intersecting minus k is bigger or equal than 0, then being Neff is equivalent to intersecting all the -1 curves non-negatively. So I claim that these are 2 and 3 are 3 is an immediate consequence of 2, 2 is an immediate consequence of 1, and for 1 it's just a matter of observing that if a divisor class intersects a -1 curve in 0, a -1 curve class can be blown down. So that means that B is actually, such a divisor class is a pullback from a blow up at one less point. Okay. This is going to be also a blow up of P2 at one less point. And then we do an induction on the Picard number. And okay, we have to prove it in the first case. Okay, so that means that that I can look only at divisors that intersect all these classes positively. And then I want to write D as minus K plus D prime. And now this divisor also has the property that it intersects all the -1 curves non-negatively. Just because all -1 curves intersect this class in 1. So we do an induction now on the degree of this divisor with respect to some fixed ample line. Okay, and that's it. Yes, that's the proof. Okay, so I want to sum up the surface case. So this already proves for Del Pezzo surfaces basically all you want to know. That so let's say the upshot of this discussion, the sum up of this discussion is that for let's say very general points, the following are equivalent. The fact that you have at most 8 points is equivalent to having finitely many -1 curves. That's equivalent to having a Del Pezzo or a surface, a blow up of P2, which has -K ample. And that's also equivalent to the surface being a Maury-Dream space. Yeah, so if it is a Maury-Dream space, there have to be finitely many -1 curves, because the point is any -1 curve will be a necessary generator of the effective semigroup. So that means if there are not finitely many of them, then the effective cone, the Maury cone, is not finitely generated. And then conversely, yes, if you have a Del Pezzo, this is a Maury-Dream space. So let me use this now to remind you what the Maury-Dream space was. So you need to check that Neff divisors are semi-ample. So they have a multiple that is base point free. Okay, so yes, you can use the same idea as here to do an induction and use the fact that -K is ample. So you do an induction on Picard number and induction on degree to prove that any Neff divisor has to be semi-ample. And you can say actually more. So these are precisely divisors that intersect all the -1 curves non-negatively. Note also that -K is the sum of -1 curves. Maybe for K equal 8, you need to take twice -K to write it as an integer combination of -1 curves. So it can be actually precise. The Neff cone is generated by what people call conics. So these are fibrations that come from classes with self-intersection 0 and the intersection is -K equal 2. You can classify them, finitely many, and then also the hyperplane class. And this is the only thing to check for a surface in order to have a moduli space, because the other condition for a moduli space was that the movable cone is a union of Neff cones on small modifications. For surfaces, small modifications are isomorphisms. So the movable cone of a surface is the Neff cone. A more general result would be that if you have in any dimension, maybe characteristic 0, if you take a divisor which has a base locus of dimension 0, then it is actually base point free. So for surfaces, it just says movable, implies movable in the sense that the base locus is of dimension 0, codimension 2 is base point free. And now you can also use these ideas to prove that the Cox ring of Del Pezzo surfaces is generated by sections corresponding to the -1 curves, and then to which you have to add, for calculate, the 2 sections of minus k. This is Batirev and Popov's proof for generators for the Cox ring. Okay, so this was the sum up for what's going on for surfaces, and now I want to go to the higher dimensional case. Any questions here? Okay. Switch ports. Meaning I go this up. Okay. Okay. Okay, so I want to go now to the high dimensional case. So the setup will be now X is a blow up of Pn at k points. And again, I will assume that they are Cremona general. Okay, so again, this just means that we are in linearly general position after any number of Cremonas. And I'll go now into the Cremonas because they show up. Okay, so now let me fix the notation of the Picard group and fix a basis given by the hyperplane class and then exceptional divisors. Corresponding to the points. And then remind you that minus k is linear equivalent to n plus 1 h minus n minus 1 sum of the exception divisors. So, and as I said, yeah, this is not Fano when k you have at least 2 points and you're in dimension at least 3. Okay, so now as for surfaces, whenever I fix n plus 1 points in linearly general position, so for any subset of n plus 1 of the points out of the k that we have, so I will assume that k is at least n plus 2. So I have a subset with n plus 1 points. I can move them to the standard coordinate points. And I can look at the Cremona transformation centered at these points. So I will call this phi I. Yeah, so if the points are the coordinate points, Okay, then this is really just the transformation that takes inverts the coordinates. So again, the coordinate hyperplane cut by xi equal to 0 will be mapped to a point, the coordinate point for that coordinate equal to 1. And then once you blow up these points, this becomes an isomorphism in codimension 1 because you can map these hyperplanes to the corresponding exceptional divisor. And so this gives you, in the end, a small modification. So it is a small modification. Yeah, small. So we'll still call it a small Q factorial modification, but it's actually just another blow up of Pn at k points. It's just that now if I have more than n plus 1 points, which I do, on the other side I blow up this x prime is the blow up of Pn at the coordinate points. And then I take the images of the other points by the Cremona transformation. Yeah, so I end up with another blow up at a different configuration of points, but it's an isomorphism in codimension 1. Okay. And then this induces an isomorphism of the Picard group of X in a somewhat non-canonical way. So I will call this phi I pullback, although it's not quite the pullback. I take this will be an isomorphism of the Picard group of X, where this is actually the factorization of the pullback map with identifying the Picard group of X prime with the Picard group of X. Yeah, so I have really an honest pullback map from the Picard group of X prime to the Picard group of X, but then here I can identify in a canonical way. So hyperplane class goes to hyperplane class, exceptional goes to exceptional. So, then this gives me a set of isomorphisms, one for each subset with n plus 1 points. And so I will define a so-called veil group, which, as Dolgachev explains in many of his papers, this goes back to Kobel, who studied this group. So this is the group generated by these isomorphisms. So we're thinking of this inside GL isomorphisms of the Picard group, GL Pic of X. Okay. Okay, so the upshot of this for us, if you are interested in the geometry of these spaces, is that when you look at the orbit of an exceptional divisor under this group, yes, as long as I consider the corresponding Cremona transformations and I follow through in an element here that I write down in terms of specific elements of the Baal group which correspond to these small modifications. So I follow through, I end up with an honest exceptional divisor on some other blow-up. So these are all divisors of the forms, I'll write like this, of the form EI or E1 on some X prime, some other blow-up. Yeah, so, yes?
So the case of the test surfaces is still allowed here?
Yes, allowed. Yes, it's all allowed. Yes.
So say for 6 points,
yes.
the cubic surfaces, would that be the Weyl group of E6?
Yes, yes, you recover, yes, of course, all the Weyl group that are associated to Delpetto surfaces. Yes, all this is applying to Delpetto surfaces, and I want to include that in this discussion. Yes, okay. So yes, we are going to prove now that there are infinitely many minus one curves on if you have at least 9 points. We're going to describe all the minus one curves for all the Delpetto surfaces, and there will be exactly these divisors. Yeah, but the point I was trying to make is that as long as you move to some other blow-up, these are actually exceptional divisors on that blow-up. So we can call these, if you want, minus one divisors. So these are the minus one curves on a Delpetto, in the case of surfaces. Okay, and now remark that all such minus one divisors are necessary generators for the effective semigroup, so either the effective semigroup of divisors, the effective cone of divisors, or the Cox ring. And the reason is that these are divisors covered by curves that intersect them negatively. So if I take a line on such an exceptional divisor, then this will intersect, when I intersect with this in X, so that's the tautological class restricted to itself, which is all minus one, and I intersect with the line. So this is minus one. So yeah, this cannot be written as an effective combination of other divisors. Okay, so at this point, yes, we proved that if you have an infinite orbit of such divisors, then the Cox ring cannot be finitely generated. Okay, so okay, so now there is a way to think of this Weyl group as an honest Coxeter group coming from a bilinear pairing. Okay, so this is what Dolgachev suggested to call the Kobel pairing on the peak of X. So this generalizes the intersection form from the case of surfaces, and it has the following form. So the hyperplane class with itself is defined to be n minus 1, the dimension minus 1, and then the pairing of the hyperplane class with the exceptional divisors is 0. And then the pairing of exceptional divisors is minus 1 for an exceptional divisor with itself and 0 otherwise. Okay, so this is exactly the intersection form on a surface, and it's so it was written like this by Mukai. My knowledge is not written like this in any other source, but this is actually what is necessary if you want to have the Cremona isomorphisms on the Picard group to come as reflections with respect to some self-intersection minus 2 classes. So this is necessary. It's the only, essentially, it's the only pairing that does that, that also has some of these geometric, let's say, natural properties, that you want two exceptional divisors, different ones, to intersect in 0. It's not hard to prove that. Okay, so as I said, this is an actual Coxeter group. Okay, any questions here? Okay. So in the Picard group X, you can look at the orthogonal complement with respect to this pairing of the canonical class. This is a subgroup that you can describe in different ways as being generated by so-called roots. So there are some classes, one for each subset with n plus 1, with cardinality n plus 1 in 1 through k. So these are alpha I is, by definition, yes, it's the hyperplane class minus the sum of EIs for I in the set I. So these are classes that are roots, in the sense their self-intersection is minus 2. And then they can associate a reflection with respect to the hyperplane cut by this root. So if you take the reflection across this hyperplane, you get this is the reflection. So okay. So if you consider these reflections for these roots, you get exactly that. You recover these isomorphisms coming from Cremona transformations. And then you can also describe a different set of generators for the orthogonal complement of K, such that the associated diagram, Coxeter diagram, is a T-shaped diagram. So this is really, they're just the group of reflections. Okay, so we already defined this. Yes, this is the Coxeter group of reflections corresponding to the T-shaped Dynkin diagram with a Dynkin type diagram that has legs of lengths 2, n plus 1, and k minus n minus 1. Okay, so here I use different roots who also generate. Yeah, so we can also see this as being generated by these roots. So these are defined like this for I between 1 and k minus 1, and then alpha k is one of the Cremona ones. Alpha, it's the hyperplane class minus the first n plus 1 exception divisors. Okay. All right. Okay, so then it's not too hard to prove that actually the Weyl group is finally generated if and only if the inequality that you already saw holds. So the point here is that this is a finite group if and only if this is a type of AD Dynkin diagram. And then that's equivalent to this inequality that 1 over 2 plus 1 over n plus 1, so the length of the legs, 1 over the length of the legs is strictly bigger than 1. So, okay, I'm not giving the proof of this, but it's not hard to see that one orbit under this Weyl group is, for example, for the hyperplane class, the degree increases arbitrarily if this condition is not satisfied. Okay, and then the theorem, which I mentioned last time, was that the condition of being a monodream space is equivalent to this condition, so the Weyl group being finite, and that's the same as the effective semigroup being finitely generated. So yeah, so this theorem makes a case in a way that the higher dimensional analog of Del Pezzo surfaces are these blowups. Yeah, so blowups of Pn at most n plus 2 and n plus 3 points, and then there are some exceptional cases in dimension 2, 3, and 4. Right? In dimension 2, just del Pesos, but then yeah, this is the correct higher dimensional analog. And then let me remark that, so whatever you can do with del Pesos, you can probably do here too. But the remark is that in this case, the effective cone of divisors, the closed cone, is generated by these -1 divisors, which are finitely many. So it's a closed cone spanned by effective divisors is a closed cone. Okay. It's not always true for the semi-group for some of the cases, but once you pass to the closure, it's true. It's just like for the case of del Pesos of degree 1, you need minus k there. So this is in this case, it's contained in the k negative side with respect to the Coble pairing, because all these classes have intersection -1 with k. Okay, and just in passing, let me say that the Lucas mentioned that you can also look at Dynkin diagrams with legs of arbitrary length. Yeah, these also correspond to products of projective spaces blown up at some points. So there also this theorem holds. Yeah, so those spaces are moduli spaces, so finitely generated Cox ring, which is also an invariant Nagata ring, if and only if the corresponding Weyl group is finite, which corresponds to this inequality. So it's actually an if and only if statement. Okay. So I want to maybe list the cases when the Weyl group is actually finite. So when it's finite, yeah, so there is the dimension 2 is just del Pesos. Blocks of P2 in at most 8 points. In dimension, in arbitrary dimension, say at least 5, or any dimension. This is the blob of Pn at n plus 2 points, or the blob of Pn at n plus 3 points. So this case is what I say, it's a classical case. This one also. This is a bit more recent. And then the remaining cases are the blobs of Pn at n plus 4 points for n equal to 3 and 4. And then the idea of the implication that if the group is the Weyl group is finite, then this is a moduli space. When you want to prove it for the cases which let's say non-classical cases, this one and this one. So the idea was given by Mukai. Okay. So there is an algebraic proof, and then there is a geometric proof. So the idea for the geometric proof was given by Mukai. Yeah, so this means finite generation of the Cox ring, or proving that these are moduli spaces by ways of geometry. So this is Mukai 2006. So for the blob of Pn in n plus 3 points, he used some results of Bauer from the 90s to describe this blob as a moduli space of parabolic bundles on P1, rank 2, so as mentioned by Brendan yesterday. So parabolic bundle is a rank 2 bundle on P1, which will split, but then you want to fix some one-dimensional subspaces in the fibers of this bundle at some points. So you say it's a parabolic bundle with parabolic structure at some points, and the number of points is n plus 3. So the fact that this is a moduli space of parabolic bundles, this is Bauer from the 90s. But then it was Mukai who exploited this idea. to actually describe all the small modifications as moduli spaces of parabolic bundles. So here you make a choice of weights to get this, and then varying the weights will give other modifications, all the small modifications. And then the similar, so he sketched also a similar idea for the remaining cases. So the blow-up of P3 at 7 points, and the blow-up of P4 at 8 points. He described these as moduli spaces of vector bundles, stable vector bundles, also rank 2, on Del Pezzo surfaces. So this would be a Del Pezzo surface which is of degree 2, and then the other one is of degree 1. And then here, what I will talk about next is actually go into how you prove this, and then, okay, by analogy, you can also see how you prove, yes? No, so, okay, so this one is, so my talk will be, I will eventually concentrate just on this part, but this is going to be a moduli space of stable vector bundles on this Del Pezzo surface. This one is on this Del Pezzo surface. And I will show that you can generalize this. But okay, so I should say that Mukai sketched these ideas. It's like, so his whole paper where he proves all these things is like 11 pages or something. But all the ideas are there. But then it took so Casagrande, Codoni, and Fanelli worked on this case of P4 blown up at 8 points. It's a 40-page paper to actually fill in all the details. Okay. So this is the case of, so Mukai's ideas worked out. Okay. Okay, so that's what, so I would like to concentrate on these ideas, and then the way they work this out and generalize this a bit. And then, but before that, let me remark that so what I'll do next is explore these ideas for the blow up of Pn at n plus 4 points. So this is not more homogeneous space if n is at least 5. But it will include also these two cases. And then the remark here is that even though they are not more spaces, their Neff cones are easy. So the Neff cone of a blow-up of Pn at k points is actually finitely generated by simple classes. This is an easy induction argument when k is at most 2n. Yes, you can do an easy induction argument arguing that there is a quadric through all the points. So these are the generators. And then again some pencils, just like for Del Pezzo surfaces. So these were the conics on Del Pezzo surface and then the hyperplane class. So this is easy to do by induction like that. But then this bound can be extended, so up to 2 to the n. So it's true the Neff cone, this part. This is finitely generated if k is at most 2 to the n. Okay, so these are results of Choshkun, Lesutre, and Autumn from around 2016. Yeah, so even though it's not a modern space, the Neff cone is finitely generated. You need to go with k okay. I think it's not known actually what happens after. Okay. All right. So the idea behind relating these blow-ups to moduli vector bundles or parabolic vector bundles is again coming from Mukai, and it is a manifestation of Gale duality, and Mukai's interpretation of that. Okay, so so maybe I want to state. Let's see. I want to state maybe a theorem that will show you a bit what's going on for the next case. So this is with Carolina Araujo, Indar Kaur, and Diletta Martinelli. Okay. So now let's say X is a blow-up of Pn at n plus 4 points. Very general, and at least 2. Okay, then you can say on the negative side of the effective cone, you understand what happens. So on the strictly k negative side, this is a cone generated by the infinitely many minus 1 divisors. These are now, it's an infinite set, if n is at least 5. So when you intersect with the k less or equal than 0, this is the closure of this cone. So these are not equal if n is at least 5. This is not a closed cone. So you can think of this as a Morricone type theorem, that on the k positive side you do not say much. So now it's with respect to the Coble pairing. But on the k negative side, you have these minus 1 divisors that span extreme arrays. Okay. Okay, then you can also say something about the Mori dream space picture, a local Mori dream space picture, except now there are countably many small modifications, but as long as you're fine with that, the picture is controllable, let's say. So there are countably many small modifications which are explicit. We can understand what happens. These are also smooth. Yes, and such that the movable cone of X on the k negative side, and with respect to the Coble pairing, is the union of the Neff cones of these models. Okay, and now there are other things you can say, that when these cones are contained entirely in the strictly k negative side, they are semi-ample, finitely generated. So this is finitely generated by semi-ample divisors if contained in the k negative side. And it's not true otherwise. Yeah, so for n at least 5, there will be classes. There will be some of these models which contain divisors which are not semi-ample on any model. In fact, for n equal, when you have exactly 9 points, the minus k class will be such a class. So it's not going to be. It's Neff on a model, but it's not semi-ample on any model. This also will recover in the case when there are finitely many of these minus 1 divisors. This will give you the so-called Mori chamber decomposition of the Mori dream spaces given by blow up of P3 at 7 points or P4 blown up at 8 points. And the geometry is explicit. Yeah? So this, the idea is this X is a moduli space of vector bundles on a blob of P2, and for a certain choice of an ample line bundle, which I'll explain. And then same holds for all these models. And it's you understand everything as long as the ample line bundle is on the k negative side. Okay. 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 So I want to say now a few words about Gale duality. Yeah, so Gale duality is a linear algebra. Yeah, so let's go step back a little. Let's do some linear algebra. So if you have k will be now n plus s plus 2 for n and s integers non-negative. So then the Gale duality says that there is a bijective correspondence between n points, k points in PS and k points in Pn for linearly general points. So I'm looking at linear general points in linearly general position. So no unexpected linear subspaces. So up to projective equivalence. And then this is in one-to-one correspondence with the same thing in Pn. Okay, linearly general. Okay, so so the idea is you can just look at do everything in coordinates. Yeah, so k points in PS will correspond to a matrix where I choose coordinates for my points. So there are some choices involved, but it doesn't matter. So this is now k by s plus 1 matrix of rank k s plus 1 maximum. Same thing for P1, Pk. This is some matrix B. This is going to be k by n plus 1. This one has rank s plus 1. This one has rank n plus 1. Okay. And then the condition that they are Gale dual is essentially the condition that there is a choice of coordinates such that the transpose of one matrix multiplied with the other is 0. So we say that these are Gale dual if, with precisely, if there is a diagonal matrix such that when I multiply the transpose of B with D with A, I get 0. So it's a k by k diagonal matrix. So it says just that there is a choice of coordinates. This D is a choice, maybe changing coordinates on one side or the other, it doesn't matter. Such that this product is of B with A is actually 0. So let's be even more explicit. So explicitly, I can choose coordinates such that my matrix A contains the identity matrix as a block of size s plus 1. And then there is some other matrix here with n plus 1 rows. Yes? it's a diagonal matrix, yes, with non-zero entries. Diagonal matrix with non-zero entries, yes. Okay. Invertible. Okay, invertible. Okay. Yeah, so I can always do this. I fix, let's say, the first s plus 1 points as the coordinate points. And then the matrix B has to be essentially, again, an identity matrix of size n plus 1. And then I take here minus the transpose of this matrix C. And so this is now, this was s plus 1, right? So this is s plus 1, s plus 1. So this C matrix is an n plus 1 by s plus 1 matrix. So this the transpose will be s plus 1 by n plus 1. Okay. So it's as explicit as that. So the points are these ones. Up to, again, projective equivalence, yes. Okay. So there is a lot of interesting geometry of how these configurations are generally related. So the case S equal 1 is already interesting. And it's saying that n plus 3 points on P1 in linearly general position correspond 1-to-1 to n plus 3 points in Pn. And now this correspondence can be made more explicit in this case. Correspondence is by taking a rational normal curve of degree n. So the Veronese embedding of degree n. So then the points, the image is under the Veronese embedding. So we are saying also that through any n plus 3 points in linear general position in Pn, there is a unique rational normal curve. Okay. And then the next case is n plus 4 points on P2 correspond to n plus 4 points on Pn, up to projective equivalence. Okay. And so now it's natural here to ask how does this play a role in the birational geometry of the corresponding blow-ups? Yeah, so the general question here is that let's say K is n plus s plus 2.
Is
So
there always such a nice geometric?
no. So as far as I know, this kind of description only holds for this case. But there are things you can say. There is a lot of geometry. Okay, so let's say I take n and s at least 2 so that I can talk about the corresponding blow-ups. So I will denote y, the blow-up of PS at k points, very general. So I'll take Q1, Qk, very general points, or in linearly general position. Then I take the Gale dual and I look at the corresponding blow-up. So these are Gale dual. Okay, so what can we say? How are the geometries of these two related? Okay, and already you can see that these are so each of them has a Weyl group that acts on the Picard group, and it's the same Weyl group that acts on the Picard group. So now we have a Coble pairing on both sides. I'm saying that you can in fact identify the roots on one side with the roots on the other on this T-shaped Dynkin type diagram in such a way that actually the roots correspond It's just a relabeling of the same diagram. Yeah, so there is a canonical isometry with respect to the Cobol pairing. So ky perp lives in it's the orthogonal complement to the canonical class of y. This lives in the Picard group of y, and then orthogonal complement to the canonical class of x. We had these roots alpha I coming from the classes on one side. These will correspond by this to, as I said, a relabeling of the same diagram. So for I between 1 and k minus 1, and then there is this leg of length 2 that corresponds to the same root. This is on y, these are on x. Okay, and so it's just a relabeling of the same diagram. And so you can identify, yes, I'm just using the fact that the diagram has n plus 1 legs on one side and s plus 1 legs on the other. And so you can identify the two Weyl groups. Okay. Okay. So then, so Mukai revisited this Gale duality from a geometric point of view. Yeah, so revisit Gale duality after Mukai. Again, you start with you have these k points on in PS in linearly general position. And then you can look at extensions of a specific type. So you look at extensions on PS of this type, where you take the ideal sheaf corresponding to these points on PS, twist by O1. And then you look at extensions of this type. So these will be some torsion-free rank 2 sheaves that appear. And then up to scaling, these are parameterized by a certain projective space. And we can compute this dimension. So these are just extensions. So the projectivization of the vector space given by x1 to the space of extensions like this. Which is the same as h1 of this sheaf. So you can compute the dimension, and it will be exactly a Pn. Okay. So we can see this. This is immediate just by looking at the exact sequence. You restrict all of 1 to the points. Yeah, so this induces an exact sequence. So the fact that the points are in linearly general position, yeah, so there is no global sections here. So you have global sections of all 1. Then all the sections, so you have k-dimensional vector space. And then you have the h1 of, so the space of extensions is parameterized by this vector space. And this is, yeah, there is no h1. Yeah, so this is k-dimensional, this is s plus 1 dimensional. And so this has to be n plus 1 dimensional. Okay. And, okay, you can actually identify. Okay, so now I claim that there is that you can think of Gale duality then as so the Gale dual points corresponding to this configuration. When you think of them as points here, will be exactly the points that you obtain from by fixing from the standard basis here. So the image of the standard basis here will be the Gale dual points. And then you can identify those as spaces of extensions. So the point Pi, the Gale dual point, this will correspond to an extension of this type with the property that the subsheaf, the ideal sheaf corresponding to the ith point is contained in F. So this torsion-free sheaf is not locally free at this point. And alternatively, you can also work on the blow-up, and there you avoid this issue of having torsion-free sheaves, not actual vector bundles. So if you work on the blow-up, then this is just basically, as I claim, this is the same as looking at extensions of the form, this time on Y, the blow-up of S at k points. You look at extensions of the form. So it was O of 1, the ideal sheaf of the points twisted by 1. So this corresponds to the hyperplane class minus the exception divisor corresponding to the point. You're looking at extensions of this, of 2 line bundles. So now this is a rank 2 vector bundle. And the point Pi corresponds to having a line subbundle corresponding to H. So here the small h, ei are the classes on the Picard group of Y. So it's a basis for the Picard group of Y. And I'm looking at those corresponding, which contain this line subbundle. And so, okay, so I'm saying that the Pn parameterizes rank 2 vector bundles on Y. So then the question is, what does the blow-up parameterize? And so I'll talk about that, and then so the general theory of stable vector bundles on surfaces will play a role here. So this is a very classical theory. And I should say the whole thing kind of begs the question of like, okay, this will work for surfaces on this k negative side. Okay, so there are several questions. One is, what if you don't work on the k negative side? There are now other moduli spaces one can consider if you're if you know more about different kinds of stability on sheaves and complexes, then it's possible to maybe extend this further. And also the other question that is interesting here is, what about Gale duality in higher dimensions? Yes, can you extend this picture? Yes, so at the level of extensions, you can. Yes, this is what this computation shows. But then, okay, so maybe stop here.